Hello, my dear. I'm inviting you to our lecture number 3 on uh, hypersonic dynamics. Okay, so today we will be continuing our previous topic called local surface inclination method. And let us start with Newtonian theory. In previous lectures, we know that the theoretical basis of Newtonian theory was developed including the centrifugal forces effect. Given the Newtonian flow model and his equation for flat surface and for curved surfaces, a precise result obtained by the rigorous application of the theoretical mechanics to the postulated model. On the other hand, when we apply Newtonian theory to practical hypersonic flow problems in air, we have seen, I also mentioned previous lecture, that the best agreement with exact result is obtained without the centrifugal force correction, which at first glance appears theoretically inconsistent. But indeed, straight Newtonian theory or Lee's modification frequently gives a very acceptable result for pressure distribution over hypersonic bodies in air, whether or not these bodies have straight or curved surfaces. Therefore, is Newtonian theory just an approximation that fortuitously gives a reasonable result for hypersonic flow? How do you think? Or is the frequently obtained good agreement between Newtonian and exact result just a fluke? The answer is no. Newtonian theory has true physical significance if, in addition to considering the limit of m became the very, very high, we also consider the limit of gamma became to 1. So let us examine this in more detail. Temporarily discard any thoughts of Newtonian theory and simply recall the exact oblique shock relation for Cp as given by this first equation on the top of this slide. Repeat it next with free stream conditions, now denoted by a subscript inversely, rather than subscript 1 as used in previous lecture. So we may write as an expression instead of the first one, Cp proportional to 4 over gamma plus 1, and expression in this bracket. If we give our equation in case of limited value Cp, in case we have very large Mach number, we may repeat it. This Cp becomes only for the first expression 4 over gamma, and only proportional sine squared from beta, right? Now, take the additional limit, and our additional limit except the very high Mach speed, and gamma became to 1. In both these limits, we have that the Cp became to double sine squared from beta. And namely, this equation is a result from exact oblique shock theory. It has nothing to do with Newtonian theory as yet. Keep in mind that beta in our equation here is the wave angle. I hope you remember this. Okay, so we have not the deflection angle. And now let us go further. Consider the exact oblique shock relation for rho 2 over rho inversely, given by this equation, repeated here, again, with subscript inverse here, replacing as 1, okay? So we get this expression. Maybe a bit complicated for the first glance, but don't worry, general, okay? So main differences you may remember as for you as this one. In numerator, we have gamma plus, in denominator, gamma minus. What the main difference is? We have only in denominator plus, okay? So these equation, it's very, very logical and so a next equation was obtained at the limit, the classical limit, when we have very, very high Mach number, and namely inversely large. So our proportion for rho 2 over rho inversely became simply for our relation between gamma plus 1 and minus 1. Okay? In the additional limit, as gamma became to 1, we can find that the same when m became to inversely. We may rewrite that rho 2 over rho inversely became the inverse value. So that is, the density behind the shock is infinitely large. In turn, mass flow consideration then dictate that the shock wave is coincident with the body shocking. And this is further sustained, which is good for our inversely, infinitely values for Mach number and very small deflection angle. So that is, the density behind the shock is infinitely large. I agree with you. Okay. In turn, mass flow consideration then dictate that the shock wave is coincident with the body surface. And this is further substantiation, which is very good for m very, very Mach number very high, and we have small deflection angle. In this case, we may rewrite beta over theta became expression only depending from the gamma plus 1 over 2. In addition, in additional limit, as we have gamma became to 1, we may certainly, when we have very high Mach number, we may rewrite when theta and beta angle very, very small, we may simply rewrite as the beta the same value as theta. In this case, we may rewrite for CP expression next simple. CP will be proportional to sine square from theta. Examine this equation. We will get the result from exact oblique shock theory, taking in the combined limit of very large Mach number and gamma became 1. However, It is also precisely the Newtonian result given in our previous lecture. So, therefore, we make the following conclusion. The closer the actual hypersonic flow problem is to the limit for very high Mach number, and when the gamma became to 1, so the closer it should be described physically by Newtonian flow. Also, in this combined limit, the centrifugal correction becomes physically appropriate. And this gives us that the Newtonian Huysman theory gives better results than straight Newtonian. For example, if you look at the right figure here, right part of the slide, this figure illustrates, for example, that the pressure coefficient over a 10% or thick biconvex airfoil for very high Mach number. And this is the same type of comparison made by in the left figure, if you see, right? But however, this right figure for gamma equals 1.5, very small line. And clearly, the Newtonian Huysman theory gives much closer agreement with the exact method of characteristics than does the straight Newtonian. And this is in direct contrast with the result, how we see for gamma as for classically 1.4. In this case, we should not expect the full Newtonian theory, properly including centrifugal effects, to be accurate, as we have seen in previous figures. On the other hand, for air with gamma equal 1.4, agreement between exact result and the straight Newtonian theory without centrifugal effect. I want to repeat another one. Straight Newtonian theory means without centrifugal effect. Okay? So this does indeed appear to be rather fortuitous. So we might ask the rather academic question. If the limit of very large Mach number and gamma became to 1, the shock layer thickness must go to 0. And then, how can there be any centrifugal force left over this 0 thickness? The answer is, of course, that in the same limit, the density becomes infinite. And also, the shock layer approaches 0 thickness, and the infinite density falls over this 0 thickness, and that is an intermediate form that yields a finite centrifugal force. As a final note on our discussion of Newtonian theory, consider this figure. Here, the pressure coefficients for a 15 degrees sub-angle wedge, as you can see in this curve, yes, angle, cone, and plotted versus pre-stream Mach number for gamma 1.4. The exact wedge results are obtained from oblique shock theory. And the exact cone result are obtained from the solution of the classical Taylor-Markov equation. This you may find in many different publications about it. I mentioned this for someone who really interested in problems of modern hyperaerodynamics. Both sets of results are compared with Newtonian theory. In this case, we may say as a Cp proportions to sine square theta. I hope you remember a couple minutes ago we mentioned this equation. Okay, so that was shown as here as dashed line in this diagram. And this comparison demonstrates two general aspects of Newtonian result. Those aspects next. The accuracy of Newtonian result improves as Mach number increases. And this is to be expected from our preceding discussion. But note that this figure that below Mach number equal 5 as a minimum hypersonic value, okay? And the Newtonian results are not even close, but the comparison becomes much closer as Mach number increases above 5, okay? And second one, Newtonian theory is usually more accurate for three-dimensional bodies, like our cone, for example. And then for two-dimensional bodies, like wedge. This is clearly evident from mainly this diagram, where the Newtonian result is much closer to the cone result than the wedge result. Please look at this diagram and be sure I'm right. Okay? So these two trends are general conclusions that seem to apply to Newtonian results for hypersonic bodies in air. Furthermore, we are tempted to say that Newtonian results for blunt bodies should use the modified Newtonian formula. And that such results usually produce acceptable accuracy as illustrated in previous figure. In contrast, we suggest that Newtonian results for slanted bodies should use the straight Newtonian law. And we observe that its accuracy might not be totally acceptable in some cases. For example, if you look at this figure, at Mach equal 20, our body's final result, the percentage error is using Newtonian result is 19 and 5% for the wedge and cone, respectively. And not as accurate as might be required for some applications. If the modified Newtonian formula had been used for our diagram here, the errors would be even larger, because in that case, Cp Mach must be less than 2. Therefore, we conclude that also Newtonian theory is very useful because of its simplicity. In some applications, its accuracy leaves something to be desired. As a parenthetical comment, this figure illustrates another trend that is characteristic of hypersonic flow. Note that at low Mach number, the exact values of Cp, exact values, expression by these equations, okay, for both the wedge and cone decrease rapidly with increasing Mach. However, at high values of Mach number, the pressure coefficient for each shape tends to seek a plateau. Yeah, in some place should be a plateau. And approaching a value that becomes rather independent of Mach number, namely at the very high value. This is an example of the Mach number independence principle to be discussed in the future lecture. There we will see that a number of properties in hypersonic flow, including CP, lift coefficient, wave drag coefficient, and moment coefficient, become relatively independent of Mach number at high Mach number. And now let's start another subtopic for today's lecture: comparison of Newtonian with exact field. The purpose of this word example is to provide even better insight into the advantages and disadvantages of Newtonian theory, especially as applied to slender bodies at small angles of attack. So vehicles designed for efficient hypersonic flight for sustained periods of time in the atmosphere will most likely to be slender shaped, and namely at small angle of attack. Is Newtonian theory a reasonable method for estimating the pressure distribution on such vehicles? How do you think? I think so. Let us take a look by considering the most slender of vehicles, namely a thin flat plate at a moderate angle of attack. Okay, and consider an infinitely thin flat plate at an angle. No, let us think at a 15 degrees at Mach 8 flow. Assume inviscid flow. Calculate the pressure coefficient on the top and bottom surface of the plate, the lift and drag coefficient, and the lift to drag ratio using first exact shock wave and expansion wave theory, and second using Newtonian theory. So let's compare the results. Let's start with exact theory solution. Consider the flat plate shown in this figure on this slide, and the flow over the top goes through an expansion wave, right? And the flow over the bottom goes through the oblique shock wave, right? And first, consider the flow through the expansion wave, we see in the plan, and using the terminology for this figure, for Mach number equal A, and using the Prandtl-Meyer function, and function it means as V1 equal 95.62 degrees, we can get expression for we can get expression for V2 as a next V. Theta plus V1. Theta we know that has 15 degrees, and these values for Prandtl-Meyer function 95, 62 degrees. So V2 get us 110.62 degrees, right? With V2 equal this value, our equation yields for our mid M2 as 14.32. So the flow through the expansion wave is isentropic. And hence, the total pressure is constant through the wave, isentropic. In each point, we have the same. Okay? So, in next, let the P naught denote the total pressure. Because the total pressure is the constant, so we may write as P naught 2 must be equal P naught 1. Okay? And we can write the static pressure ratio across the expansion wave. And next time, for a calorically perfect curve, the ratio of total to static pressure at a point in the flow is a function of the local Mach number at that point. For example, you may reference in some publication that was made of nearly 10 years ago. And that generally give us this expression. P naught over P proportional we have in the parentheses and have relations gamma over gamma without 1, this expression. So we can, hence, we may rewrite a bit complicated expression, but generally it's simple. P2 over P1, it will be proportion as before. P naught 1 over P1 over P naught 2 over P2. So we have this expression here in bracket. What we have? We have two the same identical values except Mach numbers M1 of the denomination square over M2, right? In the same power of this expression. In case we have Mach number equal A and M2 14.32, we can get the relations P2 over P1 get us this value O dot O203. So the pressure coefficient will be given by this expression equation. CP2 will be proportional to 2 over gamma M1 squared times, in parentheses, P2 over P1 without 1. Hence, we have expression for CP2. Its expression for the constant 2 over 1.44 times 8, well, 64. Expression here, O dot O203 without 1, get us values minus O dot O219. Okay? So, to obtain the pressure coefficient on the bottom surface from oblique shock theory, our expression, here, this expression, with angle of 15 degrees and Mach number of A yields a shock wave angle of 21 degrees. So beta equal 21 degrees. From our aerodynamic relation, with beta equal 21 degrees and Mach number A, and denoting the pressure behind the shock as P3 consistent, we can have expression in this case P3 over P1 get us 9.443. Okay? Hence, the pressure coefficient on the bottom surface, CP3, will be expressed by this equation. 2 over gamma M1 squared, and parentheses, as we can see, P3 over P1 without 1. Our inputs our units here, we get CP3 as expression here 0.1885. From this equation, the normal force coefficient is simply get us expression for Cn, as will be CP3 minus CP2, and in the numbers that get us 0.2104. Okay. Next time we can write Cl Cl proportional Cn cosine alpha, get us in numeric value, and we can get this expression here. And from next equation for CD, we will rewrite it will be Cn sine alpha, and that get us expression in the exact solution here. And the same, we can finally find a relation for the L to D. It will be proportional for the same area as simply for the coefficient CL over CD. And that get us 3.73 for our exact solution. Okay? But not should be noted, for more details on how to make this exact shock wave and expression wave calculation, we may get some experimental research made in several years ago. Generally, I may say, as a case in point in the preceding calculation, our last equation was used to find the shock wave angle beta equal 21 degrees. To do this arithmetically, our last equation would have to be solved by trial and error. In reality, the value of 21 degrees for beta 21 degrees was obtained from a graphical plot of our last equation, and called this usually theta BM curve. Theta BM curve. So let's see next solution according Newtonian theory. According to this, for the upper surface of the plane, we may rewrite CP2 equal to 0, right? Next, for the lower surface of the plate, we may rewrite CP3, it will be 2 sine square from alpha. Given 15 degrees, we can get these exactly result. Okay? And next, for CL, we can get example result, and for CD2. Okay? And finally, we can find relation L to T, lift to drag, the same if area is constant, and we have really constant area. So we may simply find the relation CL to CD. And because the absolutely identical value, 3.73, as in previous solution. Okay? So, what we have now? The preceding example provides some important comparison between exact theory and Newtonian. First, compare the work effort to obtain the answer. Going through the exact calculation was much more work than using the simple Newtonian theory. Indeed, the Newtonian calculations were essentially one-liner to get answers. Nothing could be more simple. Okay? And this comparison highlights the value of Newtonian theory. Absolute simplicity. But this simplicity is obtained at a cost, and namely a loss of accuracy. For example, for the pressure coefficient at the bottom surface of the plate. And we have the following. So let's see next. We have exact CP3, get this value. In Newtonian, we have CP3 a bit different, 0.134. So Newtonian theory underpredict the pressure coefficient on the lower surface by 29%. For the top surface of the plate, we have the following. In exact solution, CP2 get us negative value 0.0219. Okay? And Newtonian get us CP2 0. So Newtonian theory overpredict the pressure coefficient on the upper surface by 100% of exact. For the least coefficient, we have the following. CL in first case, 0.2032. And for Newtonian, CL get us 0.1294. So for the drag coefficient, we have the next one, this value and this value. So the Newtonian result underpredict both CL and CD by 36%. However, the values of lift to drag ratio, LD, exactly in both cases get us, look, 3.73 as exact solution as Newtonian. And this is not surprise for two reasons. First, because the Newtonian values of CL and CD are both underpredicted by the same percentile. And hence, the ratio is not affected. And second, the value of lift to drag ratio for inviscid flow over a flat plate, no matter what theory is used to obtain the pressure on the top and bottom surfaces, is simply a matter of geometry, as discussed earlier in conjunction. We discussed this, as you remember, at the end of previous lecture. From this equation, a lift to drag theory, we can write L to D as a cotangent alpha, cotangents from 15 degrees, get us 3.73. Right? A conclusion from the preceding example, as well as from the comparison shown in this figure, is that Newtonian theory, when applied to hypersonic slender bodies at small to moderate angle of attack, does not do a good job of estimating surface pressure or resulting lift and weight drop. Newtonian theory is much more applicable to hypersonic blunt. The Newtonian pressure distribution around the nose of a blunt body, you see this in this part of the right part of this diagram, is reasonably accurate, as illustrated in this diagram. You may compare it straight Newtonian and modified Newtonian solution. Okay? Now, let us analyze a lift to drag ratio for hypersonic bodies. The magnitude of the lift to drag ratio calculated in the preceding example is important to know. It is very low in comparison to those values for a flat plate in subsonic or even in supersonic flow. Here is a harbinger of things to come. hypersonic flight vehicles suffer from characteristically low values of L to G, lift-to-drag ratio. And this is not good news when designing hypersonic vehicles for sustained flight in the atmosphere. Generally, you see they have very, very small wings or even without wings at all. Okay? So the lift-to-drag ratio of a body is a direct measure of its aerodynamic efficiency. For example, everything else being equal, the higher is the value of lift-to-drag ratio, and the larger is the range of the vehicle. The design of hypersonic vehicles with a reasonable value L to G is a challenge, and even better say, it's a quest, as will be discussed a bit later in our lecture. Now, let's analyze another topic of today's lecture called tangent wedge and tangent cone. Referring again to our roadmap given in a first lecture, we remind ourselves that we are discussing a class of hypersonic prediction method based only on a knowledge of the local surface inclination relative to the free stream. The Newtonian theory discussed in previous lecture was one such example. The tangent wedge and tangent cone methods presented in this module are two others. So let us consider first the tangent wedge method, applicable to two-dimensional hypersonic shape. So consider the two-dimensional body shown as the hedge area in this slide, and assume that the nose of the body is pointy and that the local surface inclination angle is theta. Theta at all points along the surface is less than the maximum deflection angle for the free stream magnet. Consider point I, we have here, okay, is on the surface of the body. And we wish to calculate the pressure at this point I. The local deflection angle at this point is theta I. Imagine a line from tangent to body, as we can see in the dotted tangent to body at this point I. How did I write? We should be found the perpendicular in this point and find the tangential. Okay? So, and this line get us an angle theta sub I with respect to the free stream and can be imagined as the surface of an equivalent wedge with a half angle of theta I. Okay? As shown by the dashed line here. So, the tangent wedge approximation assumes that the pressure at point I here in this is the same as the surface pressure on the equivalent wedge at the free stream Mach number. Free stream Mach number M inverse. Okay? That is, Pi in this point is obtained directly from the exact oblique shock relation for a deflection angle of theta sub I and the Mach number as we have. So the tangent cone method for application to axisymmetric bodies is analogous to the tangent wedge method and is illustrated in this way. As you can see, generally, it's not a big difference. Consider we have a point I on the body here, and a line drawn tangent to this point and make the angle theta I, theta sub I, okay? With respect to the free stream. Shown as the dashed line here, this tangent line can be imagined as the surface of an equivalent cone with a semi-angle of theta sub I. The tangent cone approximation assumes that the pressure at point I is the same as the surface pressure on the equivalent cone at a Mach number for the beginning. And that is pi pi in that point is obtained directly from the cone table. Okay? Nice. So both the tangent wedge and tangent cone missile are very straightforward. However, they are approximate missile, not based on any theoretical ground. And we cannot derive this missile from a model of the flow to which basic mechanical principles are applied. In contrast to the theoretical basis for Newtonian flow. But nevertheless, the tangent wedge and tangent cone missile frequently yield reasonable results at hypersonic speeds. Why? Because we can give an approximate hand-waving explanation as follows. And first, consider a line drawn perpendicular to the body surface at point I, okay, perpendicular to vertical in this, and across the shock wave layers as sketched in this diagram. But note that the imaginary shock wave from the imaginary equivalent wedge crosses this line below the point, where the actual shock wave from the body crosses the line. And the region around this line is isolated and imaginary, and magnified. And you can see in this diagram, I magnified it. And now consider the following fact. And fact is next. In the hypersonic flow, an oblique shock wave on a slanted body, the y component on the flow velocity v is changed much more strongly than the x component of u. Okay? And this fact, which we will revisit several times in the following module, is proved by a combination of our equations, and which yield in the limit of very large number, referring to shock geometry as we can see here. So we might found our relation next. du over v, it scatters v infinitely minus u2 over initial. And we can simply express as a gamma plus 1 over 2 times theta squared. And the next relation, dv over v infinity, will be expressed as v2 over v infinity, and will be became to simply the theta n. So in our first expression, du is the change in the x component of velocity across the oblique shock. In next expression, delta v is the change in the y component of velocity. Clearly, the change of the v velocity is considerably smaller because order of theta squared than the change of the u velocity, Yeah, because u velocity order of simply of theta. But keep in mind that theta is a small angle in radial. Okay. In turn, recording Euler's equation as a here dp proportional minus rho v dv, and this implies that the major pressure gradients are normal to flow. Normal means perpendicular. And referring to this last equation, the principal change in pressure is therefore along the normal line. Here we may write as the I in I back B, I for the A and B relation. By comparison, changes in the flow direction are second order. And hence, examining this figure, the surface pressure on the body at point I is dominated by the pressure behind the shock at point A because of the centrifugal force effect. And the pressure at point I, exactly when the going book, will be Pi, okay? And will be less than pressure in point API. Now, the tangent wedge method, we may write Pi should be equal Pb, where Pb is the pressure behind the imaginary wedge shock. And the pressure Pb is already less than Pi. Yeah? Because the imaginary wedge shock angle at point B is less than the actual body shock angle at point A. Okay? So beta body higher than beta wedge. Beta body and beta wedge. And thus, we see that the wedge pressure Pb is a reasonably approximation for the surface pressure Pi, because in the real flow picture, the higher pressure Pi behind the body shock is mitigated by centrifugal effect, as the pressure is impressed from the shock to the body at point I. The same reasoning holds for the tangent cone method. Result obtained with the tangent cone method as applied to a pointed ogive are shown in this slide. And here the surface pressure distribution is plotted versus distance along the ogive. Ogive form, as you can see in this picture. What set of results are presented, each for a different value of k will be proportional m infinitely and times d over L, where d over L is the slenderness ratio of the ogive, L and d, okay? And we have S ogive. The solid line here in this diagram is an exact result obtained from the rotational method of the characteristic. And the dashed line is the tangent cone result, where a reasonable agreement is obtained, and thus illustrating the usefulness of the tangent cone method, albeit it's a rather tenuous foundation. The same type of agreement is typical of the tangent wedge method. In this figure, the parameter K is proportional for Mach number, and DL ratio, yeah, we call here in our case slenderness ratio, sometimes called the hypersonic similarity parameter. and its appearance is simply a precursor to our discussion of hypersonic similarity in next lecture. Okay? And now let's come to the shock expansion method. Of the local surface inclination method discussed so far, the Newtonian method can be applied to a body surface of any inclination angle, whereas the tangent wedge or tangent cone method require a local surface angle, but less than the shock detachment angle for the given free stream Mach number. This is why Newtonian theory can be applied to blunt nose sides. But the tangent wedge and or tangent cone method are limited to sharp nose body with attached shock wave. The method discussed in the present other module, the shock expansion method, is in the latter category. It assumes a sharp nose body with an attached shock wave. However, it has more theoretical justification than the tangent wedge or tangent cone method, as will be described. So, consider the hypersonic flow over a sharp nose two-dimensional body with an attached shock wave at the nose as sketched in this picture, in this slide. The deflection angle at the nose is theta m, okay? The essence of the shock expansion theory is as follows. First of all, as assumed, the nose is a wedge with semi-angle theta m. Calculate Mach number and Pn, Mn, and Pn behind the oblique shock at the nose by means of exact oblique shock theory. Second, assume a local Frank-Meyer expansion along the surface downstream of the nose. We wish to calculate the pressure at point I, okay? So we want to find Mach sub I. And this is obtained from the Frank-Meyer function, assuming an expansion through the deflection angle delta theta. Delta theta is the difference between theta m minus theta I. So delta theta may be calculated as this large expression here on the slide. Very large and maybe not convenient for us, but generally it's not difficult because here we all have analogous using here gamma -1 and gamma +1 in first part positive in upper time in down, in next time opposite the same gamma, and after that we simply have the Mach number n squared -1 and Mach number L squared minus. In this equation, m sub I is the only unknown. Mn in this equation is known from the preceding step 1. And delta theta here is known geometrical quantity, okay? Of course, for air with gamma equal 1.4, and tables for the Frank-Meyer function about this would be used to calculate m sub I. But rather than attempting to solve this exact equation. And now, third, calculate Pi from the isentropic flow relation. According to this relation, Pi over Pn get us this expression, more simple, inconvenient than trivial one. Okay? Again, for air with gamma equal 1.4, the isentropic flow tables can be used to obtain Pi in a more convenient manner. Agree? Okay, let's go in. So, result from the shock expansion method obtained from some experimental work for flow over 10% thick by convex airfoil, shown in this diagram, as compared with the exact method or characteristic. Excellent agreement is obtained here. This is to be somewhat expected. After passing through the attached shock wave at the node, the actual flow does indeed expand around the body. And this expansion process is approximated by the assumption of a local frontal Maya expansion. Why this is not a precisely exact calculation is discussed in 2 steps before. Okay? So, the shock expansion method can also be applied to bodies of revolution. The method is essentially the same as shown in this figure, except now theta n is assumed to be the semi-angle of a cone, and mn and pn at the node are obtained from the exact Taylor-McCall cone result. Then, the frontal Maya expansion relation are applied locally downstream of the cone, downstream of the node, sorry. And this implies that the flow downstream of the node is locally two-dimensional, which assumes that the divergence of the streamline in plane tangential to the surface. For bodies of revolution at 0-degree angle of attack, this condition is usually met. Results for shock expansion method applies to ogive at 0 angle of attack and shown in this figure A. The ogive has a slenderness ratio, I hope you remember, at D to L, 1/3. In A figure on the left side, the results are for the supersonic Mach number 2.73. Whereas in next figure on the right, this Mach number equals a bit higher than 5. The circles are experimental data. The solid line represents an exact result from the method of characteristics. And the dashed line here is from the shock expansion method. Note that for the supersonic case, the shock expansion method yields poor agreement. However, for the hypersonic case, the shock expansion method is much closer to the hypersonic case. And the shock expansion method is much closer to the exact result. There is a reason for this, as explained in the following. Consider from this figure, which contains schematics of supersonic and hypersonic flow over a pointing body with an attached shock wave. Downstream of the shock wave, expansion waves are generated at the surface of the body and propagate outward, eventually intersecting the low shock wave. And this expansion wave reflects from the shock wave. the reflected wave propagates back to the body surface, as shown by the dashed line in this figure. Shock expansion theory ignores the effect of these reflected waves on the body surface pressure. Now, consider just the supersonic case sketched in the left figure, in figure A. At supersonic Mach number, the shock angles and the incident and certainly reflected wave angle are large, because the incident and reflecting waves are essentially Mach waves. With the Mach angle, I hope you remember, mu, it will be arc sines from 1 over Mach number. Okay? Where our Mach number is the local Mach number. At low Mach number, mu is very large. As a result, as you see in this left figure, the reflected wave influences a considerable point of the body surface. And this influence is not taken into account by the shock expansion method. In contrast, for the hypersonic case, shown in the right figure, figure B, the shock and Mach angle are much smaller, and the reflected wave propagates much farther downstream as they hit the body surface. So, as a result, the reflected waves do not greatly influence the surface pressure, especially on the forward portion of the body. And therefore, the real hypersonic picture satisfies the assumption of shock expansion theory more closely than the supersonic picture. And it is no surprise that shock expansion theory yields better agreement at higher Mach. Now let's become to summary. In this lecture, has deal with hypersonic local surface inclination method. Such method predict the local surface pressure as a function of the local surface inclination angle relative to the free stream direction of theta. The method discussed were, first of all, the straight Newtonian method, which yield this first expression, Cp proportional to sine squared theta. Second, the modified Newtonian method, which states the Cp proportional Cp maximum, and the same sine squared theta. And third, the Newton-Boltzmann method, which takes into account the centrifugal force correction. And for our two-dimensional body, this result will be described by this expression, this integral. And next, fourth, the tangent wedge method, where the pressure at point I on a two-dimensional body is assumed to be the same as a wedge with deflection angle theta. Okay? And next, 5, the tangent cone method, where the pressure at point I on an axisymmetric body is assumed to be the same as a cone with a semi-cone angle of theta I. And next, 6, the shock expansion method, where the pressure distribution downstream of the attached shock wave on a 2 or 3-dimensional body is assumed to be given by a local Prandtl-Meyer expansion. It is not possible to state with any certainty which of the preceding method is the best for a given application. All of these methods have their strengths and weaknesses, and some intuitive logic is required to choose one over the other for a given problem. For example, if the prediction of the pressure distribution over a hypersonic airplane, any distinguishable portion of the fuselage might be treated with a tangent cone missile, whereas the wing might be better treated with the tangent wedge missile. Of course, for surface with large inclination angle, I mean greater than the maximum deflection angle for an oblique shock wave at the given Mach number. So the Newtonian method is, in this case, appropriate. Within the confines of the Newtonian method itself, for blunt surfaces where theta is very large, modified Newtonian is best, whereas straight Newtonian usually yields better results for slender bodies. In both cases, for gamma equal 1.4, the centrifugal force correction leads to poor results and should not be used, because you should keep in mind that also the centrifugal force correction is theoretically consistent with mechanical principles. And it is quantitatively correct only in the combined limit, when we have combined limit at the bottom here, when we have very large Mach number and when the gamma became to 1. So in regard to all of the local surface inclination methods discussed here, none of the preceding judgment on accuracy and applicability are totally definitive, and they all must be taken in the split of suggestions only. However, one definitive statement can be made about all of these methods, namely that they are straightforward and easy to apply. For this reason, they are popular design tools for the investigation of large numbers of different hypersonic bodies. Indeed, all of the local surface inclination methods in this part of our lecture are embodied in an industry standard computer program called the Hypersonic Arbitrary Body Program, originally prepared by Gentry, and for this reason frequently referred as the Gentry program. This program has been in wide use throughout industry and government since the early 1970s. So very, very old. All of these methods discussed in our lecture are options within the Gentry program, which can be called at will for application to different portions of a hypersonic body. And this program, and moreover, a modified version of it, is widely used in the preliminary design and analysis of hypersonic vehicles. It is mentioned here only to reinforce the engineering practicity of the methods discussed today. So let's start with one design example. This is the first of a number of design examples of our lecture. The main thrust of this lecture is to present the fundamental aspect of hypersonic and high temperature gas dynamics. We will from time to time, however, size the moment of elaborate on the design application of the fundamental. And namely, this is such a moment. The Hypersonic Arbitrary Body Program, HABP, Hypersonic Arbitrary Program, an elaborate computer program for predicting the surface pressure shear stress, and heat transfer distribution over hypersonic bodies of arbitrary shape, as well as their lift, drag, and moment coefficients, uses the local surface inclination method discussed in today's lecture. In fact, HABP, Hypersonic Arbitrary Body Program, offers a choice of 17 different pressure prediction methods. But the primary ones of the choice are Newtonian, modified Newtonian, tangent wedge, tangent cone, and shock expansion, all discussed today. So methods used for the prediction of shear stress and heat transfer are discussed today. And the purpose of HABP, Hypersonic Arbitrary Body Program, is to provide an easy-to-use, fast, and reliable hypersonic aerodynamic prediction code for use in the preliminary design of hypersonic vehicles. Developed by the Douglas Aircraft Company in 1964, the code was greatly expanded in 1973 and then further updated in 7 years in 1980. As mentioned earlier, this code is frequently referred to as the Gentry program after one of its originators. The HABP, or Hypersonic Arbitrary Body Program, is still in use today as a preliminary design tool, especially in USA and Canada. An interesting and completely independent evaluation of HABP was made by Karen and Fisher of British Aerospace plc. In this slide, Fisher presents calculations made with Mark IV version of HABP for a variety of different vehicle configurations for which experimental data exists. In HABP, the vehicle surface is divided into a large number of flat surfaces of panels. For example, this figure shows the paneling used to represent the geometry of the space shuttle. Knowing the free stream Mach number and the angle of inclination of each panel relative to the free stream, a chosen local surface inclination method is used to obtain the pressure coefficient on each panel. The curve label 1.1, when k equals 2, pertains to item 1, modified Newtonian. For the windward side and item 1, Newtonian when Cp equals 0 on the leeward side. And k is a modified Newtonian correction factor given by Cp proportional as a k sine squared from theta, remember. So hence, k equals 2. And hence Cp will be equal 2 sine squared from theta, remember, which is really the straight Newtonian result. And the curve label for the k equal 181 is the same set of the method, except with a different value of k. So we may write here as Cp equal 181 sine squared theta. The curve label number 14 uses the Thalem-Bach imperial method. It was not described in our lecture. For the windward side as the Newtonian when Cp equals 0. This result for the leeward side. And finally, the fourth curve uses 6.4 inclined form for both the windward and leeward sides of the ogive portion of the vehicle, and 3 and 2 when k equals 1.81, tangent wedge for the windward side, and a combination of modified Newtonian with k equals 180.81, and Prandtl-Meyer for the leeward side of the cylinder tail portion. Comparing the results shown in this diagram, this first curve gives the best agreement with experiment, illustrating the value of mixing and matching various options available in HABP for different parts of the vehicle. The normal force coefficient C sub f is accurately predicted, and the location of the center of pressure XCT and the moment coefficient above the node C sub f are reasonably predicted. So all of the pressure predicted method underpredict the axial force coefficient C sub A because skin friction is not included in their particular result. And also, we should keep in mind that the result shown in this diagram for Mach number, as mentioned here, 4.63, is relatively low Mach number for applicability of local surface inclination method discussed in our lecture. No, because generally speaking, classical or typical hypersonic flow, we mean when the Mach number higher than 5, okay? So return to this slide, which shows the panel distribution for a space shuttle calculation. You see in several panels that using in our calculation. And predicting aerodynamic data for the space shuttle at Mach 13 and a half obtained from HABP are compared with wind tunnel and flight data in this slide. The prediction from HABP used only one combination, 1.1 when k equals 2, and that is straight Newtonian. Proposed slide gives the various of variation for Cn, Ca, Cm, Cd, Cl, and lift to drag ratio as the output. Yes, you see, lift to drag ratio as a function of angle of attack. The wind tunnel data span the complete angle of attack interval, whereas only one flight data point is shown on each graph. Because Mach of 13 and a half pertains to a specific point on the entry flight path, and hence to only one specific space shuttle angle of attack. Okay? For the most part, the HABP calculations are markedly close to the wind tunnel data over the range of angle of attack. The flight data given here from STS-1, Space Shuttle 1, but some of the coefficients deviate slightly from both the wind tunnel data and the HABP calculation. But overall, we can see that HABP is a useful engineering prediction code for the space shuttle aerodynamics. So why today we have so many sources for calculation in hypersonic flow? And this statement is reinforced by the data shown in this slide. Here the lift, drag, and moment coefficients, and even the lift to drag ratio for the space shuttle are given as a function of Mach number. As the shuttle flies down its entry flight path. The flight data from STS-5 are given by the circle, and the pre-flight predictions are given by the triangle. Calculations using four different methods from HABP are also shown in all these four figures. The discontinuities shown here are caused by shuttle maneuvers, which are not accounted for in the calculation. The two HABP methods labeled with shielding refer to the shielding option in HABP, which accounts for the reduction in pressure on an elemental panel that is shielded, and namely hidden from the free stream flow by another panel. For such shielded panels, the pressure coefficient is set to 0. Clearly, from the result shown in this slide, HABP gives a reasonable prediction of the space shuttle aerodynamic characteristics, except for the moment coefficient. The discrepancy in the moment coefficient calculation is caused by flow field chemically reacting effect, not included in our HABP, and not reflected in the NASA pre-flight prediction data, which are largely based on cold flow hypersonic wind tunnel tests. Very recently, at the NASA Ames Research Center developed a new aerodynamic prediction code labeled CBAERO, the configuration-based aerodynamic software package, much in the same spirit as the earlier HABP. This new code makes pressure predictions using the modified Newtonian, tangent wedge, and tangent cone methods discussed in today's lecture. In contrast to HABP, however, this new solve uses panels on the body surface that are an unstructured mesh of triangles, such as shown in this slide, for the surface of the space shuttle. Compared to rectangular panels, this surface grid of triangles allows a more precise definition of complex vehicle geometry. Moreover, existing unstructured mesh generation programs developed for use in computational fluid dynamics, CFD, can be used here for the body surface tunneling. Indeed, this allows using this new source result to be compared more directly with CFD computational fluid dynamic result using the same method. And namely, in this figure, the shuttle surface is covered by more than 100 triangles. It's using that modified source. Other modern features contained in new source are the inclusion of high temperature equilibrium, chemically reaction flow, thermodynamics, the engineering prediction method of Taube, as well as the reference temperature method for convective aerodynamic heating, and an engineering method for stagnation radiative heat transfer. This will be discussed in our final lecture. So be patient, okay? And all this I just said, all this allows the use of class modified source to predict the surface pressure, surface shear stress, convective heating, and radiative heating for vehicles operating in the severe aerothermal environment associated with flight Mach number as high as 36, that associated with Apollo-like atmospheric entries for a lunar mission. Kinney and Garcia from NASA computed surface pressures along the top and bottom center line of the space shuttle at Mach 24.87 and at the angle of attack of 40 degrees. Exactly, it will be 40.17 degrees. As all of this given the result in this slide. Two sets of results are shown. One obtained from modifying CBAERO top, and the other from a detailed CFD flow field solution using a NASA Ames Research Center code labeled DPLR. The local surface inclination pressure prediction method in most modern soft CBARO agrees very well with the CFD result for both the windward surface, the upper half, and the leeward surface at the lower half. The lateral pressure distribution over the perimeter of a cross-section of the space shuttle body are given in this one. The body cross-section is located 8 meters downstream of the node. The pressure distribution is plotted versus the lateral coordinate y and for a looped curve, because at any given lateral location y, there is a surface point on the windward side and another on the leeward side. Okay? So the upper part of the loop for the higher pressure corresponds to the windward side, and the lower part of the loop, or the lower pressure, corresponds to the leeward side. And here we see that CBAERO slightly over-predicts the peak pressure of the windward side, especially along the side portion of the body with large lateral cavity, where three-dimensional flow effect a bit strong. Sorry, it's not be exactly big. It's maybe sometimes maybe very, very. Results obtained in a more severe aerothermal environment are given for the space shuttle illustrates the triangular panel distribution over the surface of the model. Here, for example, we have 29,000 triangles that use for calculation. So, in general, the CBARO does a reasonable job of predicting the Apollo command module pressure distribution. And result obtained for an even more severe aerothermal environment are given for the Project Fire 2 test vehicle. And this figure illustrates the triangular panel distribution over the vehicle surface. And here we have many thousand triangles that used for calculation. The calculated center line pressure distribution for the test vehicle at Mach or given at 24.87, and the angle of attack of 40 degrees is shown in this. This result from CBAERO compared with a CFD DPLR, generally it's a CFD result. So the two modified CBAR result compare very well with our detailed CFD calculation, except in the shoulder region, where CBARO slightly over-predict the pressure. And we can see on this one, okay? And we end this design example with an example of CBARO used for the optimal design of hypersonic vehicles. This example is taken from the work of Kinney, starting with the HL-20 through crew transfer vehicle shown in this slide at Mach 20. So, an angle of attack of 20 degrees as a base line. Kinney obtained the optimized shape shown in this slide at the same Mach number and angle of attack. An angle of attack 20 degrees was chosen because the baseline HL-20 has a maximum value of lift to drag ratio of 1.5 0.14 at this angle of attack. The objective of the optimization is to maximum lift-to-drag ratio while holding the volume of the vehicle constant and constraining the pitching moment to 0. The optimized shape in this figure has a lift-to-drag ratio 2.78, almost twice that of the baseline vehicle. Recall that in the optimization procedure, the angle of attack is held constant at 20 degrees. Curiously enough, Kinney found that the resulting optimized shape in this figure has a maximum lift-to-drag ratio as 3.24, and that is occurs at an angle of attack near 15 degrees, comparing the optimized shape in this figure with the baseline HL20 in previous slide. Kinney observed that the optimization process drove the optimized geometry toward a wedge-like configuration on the forward portion of the body, and that the windward side of the vehicle took on a wave rider-like shape. He also noted that the fin took on a smooth dihedral shape and were reduced in size. So, in conclusion, at the time of writing the local surface inclination method discussed in today's lecture, also developed for hypersonic applications in the 1950s, how many years ago, are certainly alive and well today. Indeed, they are the basis of the modern configuration-based aerodynamics prediction code, CDAERO, highlighted today, as well as the well-established hypersonic arbitrary body program, HABP, we discussed earlier. Okay? So next lecture will be hypersonic inviscid flow field, and I hope this is enough for today. I hope you enjoyed this lecture, and I'm really looking forward to seeing you next time. Bye.